Alright, so hi everyone. My name is Jose Gomez. I'm from Spain. I'm doing my master's in civil engineering, and well, I've been the coordinator of the 2016's SMILab summer camp. And well, first of all, I wanted to say that it's been a pleasure to work with you two guys. I think it's been very encouraging for you and for us to learn from you and see how determined are you to work in the summer where you could be doing anything else. And yeah, I think we encourage you to pursue an engineering-related degree. I hope this summer has made the decision a little easier. And well, I'm gonna hand it out to Manny, who's gonna talk about continuing research on sensor usage for railroad bridge inspection.
And there are cookies and drinks there. I saw some cookies.
Okay, so my name is Emmanuel Rivas. My mentor is Jose Gomez, and this is my presentation on continuing research on sensor usage for railroad bridge inspection. So first, I'd like to give an outline of the presentation. I'm going to be talking a bit about the background, our preparations, our structure ideas, setup ideas, our beginning structure that we designed, some of the flaws it had, and then the next structure we designed, some of the methods we used to retrieve and process data, our results and analysis of that, and then our conclusion. So starting out, I came here, I didn't know much, so I've had to learn all the equipment and all the programs that we're going to be doing. So the first two sensor boards, the most important parts of this research experiment, are the Arduino Uno and the IMU 6 Degrees of Freedom sensor board, and I'll talk those in the next slide. The Arduino is processed by a program called the Arduino IDE program, and that's how the sketches are created. We use the Quanzer shake table to simulate our wave functions that simulate our bridge movements and our railroad movements. To graphically analyze the data, I use Microsoft Excel program, and we also use basic workshop tools and parts to create our structure. So to begin, our board details. So the Arduino Uno microcontroller board is a microcontroller board, and it's basically like a small computer. It's used to receive inputs that could be digital or analog, and it can process those inputs and send specific outputs depending on what you want and how you programmed it. And we linked up the Arduino to this sensor board here. This is the IMU 6 Degrees of Freedom sensor board. And this board contains two sensors on it, the ADXL345, which is an accelerometer, and the ITG3200, which is a gyroscope. And we would be using those two sensors, processing it, sending it to the Arduino, and then sending it to the computer. So to prepare like the early stages, we would have to find a sketch. This is an example of the Arduino IDE program, what the format looks like, and it uses basic coding language, and we would find our sketch online, modify it to our needs, just like think of what kind of data we wanted to receive. And then the thing about the Arduino is it receives many samples per second and many bits of data. And we had to adjust that through the sampling rate, determine what terminal we wanted to use and how much data we wanted to receive per second, basically. And the hardware, this right here is a breadboard, and this is where we mounted our sensor onto it, and you'll see that in another photo where I showed the sensor. We mounted the IMU sensor onto it, connected it with basic breadboard wires, and then connected that to the Arduino. So you can see the basic process. So that blue platform right there, that's the shake table, and Jose would send data to the shake table. It would cause movements, and you can see the two plates, you'll see it better later on. It contains both the sensors that we were using, and it would process the movements of the shake table. I would take that data, put it into Microsoft Excel, and then make a graph of that data and sort of analyze or observe what's going on. And Jose offered that I could use the program MATLAB, but it's quite complex and it would take a while, so Microsoft Excel would be the best way to process my data. Now we did some beginning experimentation to see how we would use these sensors. So as you can see, this is the shake table up top, and like some beginning experiments, we mounted both sensors. On the left you can see my sensor. On the right, that is Jose's sensor, which is solely the accelerometer, but it's a better version of my accelerometer, but it doesn't contain the gyroscope. And this in the middle, this is the LVDT, this is our control. This is what we would be comparing our sensors to. It's a displacement sensor, it's very accurate, and it's also quite expensive compared to our sensors. So we would do some earthquake tests, we would do some calibration experiments, and we would tilt the sensors depending on like a specific degree, and we would check the accuracy of the sensors. And then we would apply a complementary filter, and then I'll explain what that is later on because that's a very important part of our experiment. But aside from this, this is just a setup, and we need to create our actual setup that we're going to use for our main experimentation. And this is going to be an abstract of that design. So I'm going to explain what this diagram is. So basically this grid line right here, this is the floor, and the blue rectangle represents the shake table. Now, we wanted the shake table to move horizontally because it contains the simulations of the waves and the movements of the railroad. So that's going to be moving horizontally depending on the vibrations or the frequencies or whatever we want to send it to. And what this basically is going to represent in Jose's idea is this is going to represent a bridge, but upside down. So what would happen is we would have these three beams here, and since they're stabilized to the floor, they're basically the ground. And right here, this shake table, which moves, this would be the deck of the bridge that the trains are traveling on and causes it to move. And this red bar right here is the pier of the bridge, which moves along with the deck. So our new structure, it needs the ability to move with the shake table because that's the point. We need to test the safety of our bridges and how much they're being displaced. But the pier must also rotate because the point of this, the sensor is going to be located on the pier. And what the sensor is going to do is it's going to measure the angular data. So we had the LVDT, and that was measuring the horizontal data, but we want to receive the same information using angular data. So what the pier would have to do, it would have to rotate depending on its reference to the ground or the shake table. And then because it's rotating in that fashion, it has to compensate for the length that it's compressing or decompressing. So I'll show our first design right here. This was our first structure. You can see the three beams right here that are stabilized onto the ground. They represent the floor. And you can see we had one rod in the middle that represents the pier, which we would put our sensors to, and this was connected to the shake table and the ground through hinges. Now see, the problem with this is that we didn't account for the compression or the decompression of the pier as it moved in that fashion. So it would be too rigid to move properly, and we wouldn't be able to use that for angular measurements. So what we did do instead is that we created a new design, and this involved two PVC pipes that slid within each other. So as it moved horizontally but also rotated in that angular form, it would slide in and out of each other, and it would take that horizontal movement and interpret it into angular measurement. And this structure was very good. It was a good design, but we could also work it better. Like for example, the way the plate that holds the sensor is mounted onto those pipes. Instead, maybe we could have it to be square. Like it still slides in and out of each other, but maybe like a flat surface to place our sensors on. But it was still a good design. It was able to achieve the results that we wanted. So this is the process for that angular data. So the complementary filter is very important because what this does is this takes the measurements that the sensor reads and it interprets it into an accurate angular measurement. So for example, here's the filter. So the angle that we want to measure is given by 0.98 multiplied by the gyroscope data that was given, and that's multiplied by the rate of time, that's dt, so we're receiving samples per second. And then that's added to the previous angle that was received, so we're receiving all this data every single second. And then this is also added to 0.02 multiplied by the accelerometer's data. So what this would mean is that we would be using 98% of the gyroscope's data, of the angular data that was given by that. But the thing about the gyroscope is it's a very accurate sensor, but it also drifts over time. And that creates an inaccurate reading over time. So this 2% of the accelerometer data fixes that drift, and it creates a better measurement over the long term. So now, how can we take these angles and correspond them to the horizontal movement of the shape table? Because that's the whole point. We want the displacement of the deck of the bridge. So here's how we use our methods and our formulas, and we create a measurement of that displacement. So if I took the diagram from the previous, so we have the shape table moving left and right, and we have the pier that rotates along with it. So what happens is that as the sensor is mounted onto the pier, it records the angular data every so often, and it takes that measurement, and what you see, this kind of forms a triangle. And what we can do is we can use a tangent formula to measure the amount that the shake table has moved horizontally. So for example, in 25 milliseconds, if we measure an angle, then what we do is we take the number of that angle at that point in time, and we could implement it into the tangent function. And then this part, the adjacent side, which is also part of the tangent function, this is the measurement of the pier. And since we can already find the height of the pier, we can basically put those two numbers in, and we can find the displacement and the amount that the deck of the bridge has moved. And that's how we found our displacement measurements. So as you can see, here's a couple graphs from our final results. This first experiment we just took, it has the same PVC structural setup. It uses that setup. We have the sensor that's mounted onto the board and reading the angular data. So what we have here is we're taking the real, which is the measurement using the LVDT, the very expensive sensor that's very accurate, and we're comparing that to my sensor plus its gyroscope in the complementary filter, and also the second one down, Jose's sensor, also added to my gyroscope and using the complementary filter. And you can see when the sine waves are created, it's a very accurate function. But the thing about this is that this sine wave function was only created for a short period of time. So we needed a long period function to see how much the measurement actually drifted away from the graph. So what we have here is the same thing. It has a wave, it has a curve, but it also includes noise, and it's basically a simulation of a train moving across the deck. And what's very important about this graph here is that we have the real measurements, and what some sensors would do is they would account for the noise that was created, but they wouldn't read that curve. They wouldn't read that static displacement. So what our sensor was able to do was follow that curve with some drift still there, but that can be fixed later on, or that can be accounted for. But the important part is that it's able to follow that static displacement and that curve right there. And then from these results, what we can obtain from our conclusion is that this new method is quite accurate, and it can be introduced as a new method to record the displacements. It's much more cost effective and practical than other methods. For example, the LVDT, that one sensor, it requires like some sort of reference point, and it's very expensive. So not only would we need to buy those, but we'd also have to create some sort of scaffolding or something to connect it to the ground or a reference point. While our sensor can be attached straight onto the bridge, straight onto the pier, and it would take those angular measurements and come up with an accurate reading. And to improve upon this, we can add better sensors, we can experiment with better sensors using that same method. And of course, if that works later on, then we could implement a wireless way of receiving that data, and that would create a very efficient and useful way of inspecting and measuring the displacement of our bridge railroads. So I'd like to thank you all for listening.
Congratulations, Manny and Jose, for a very interesting presentation. So, when people do presentations, we allow the audience to make questions.
Oh yeah, of course, questions.
So anybody, who wants to ask Manny?
I have a comment.
Yes.
You're a really great speaker,
Thank
and
you.
you explain things very well. So I appreciated that.
I don't know if I have a question that would be not, I don't want to say dumb, but but when you take it from here, how do you go to physically trying it out and saying, okay, we're going to go place it somewhere out there? Like, how do you run from here to that?
So he's already tested on the laboratory. So he comes here, meets with Jose. It's not magic. They've been working hard
Right.
to what they prove here. And it's a physical little bridge. What they don't explain, Jose, that in earthquakes, we use the shake table to move the ground. And now he's turned it around. So now the ground is on the top and the railroad is on the bottom. So we're already doing something physically. The next thing would be to go down to Belen in New Mexico. We have contacts with the railroad there, and we can bring our little engine, because we need the power, and attach these sensors, and we can put a little LVDT, like a tripod with the camera, that would be of our fixed point that you have here on the lab, and we would also have his sensors. And we would compare if his sensors can measure a real railroad bridge vibrating the train vibrating the railroad bridge with the fixed point. So we'll stay in touch. It sounds like your mom wants to go a little further.
That's interesting, yeah.
So I think maybe, I have some comments, but I can talk with you later. I think one thing, when you go to the filter in slide 13, if you can go back, you explain. That's new for me, because unfortunately I haven't been here around too much, and it's something complicated that I wasn't aware of. So you're already correcting an offset that you're getting with the tilt, and you're using the accelerometer? Or how did you find out it was 98 and 2?
Yes, well, the complementary filter, the default is 98 and 0.2. Like, it gives it that way. That's
This technical
If you find,
specifications?
when you look for complementary filter in Google, you just see that a recommended setup is that one, 98% and 2%, because it's an intermediate point between correcting the drift of the gyroscope and correcting the noise of the accelerometer. But of course, you can decrease it if you have a very good accelerometer, or that's why it says that it can be adjusted. You can tune it depending on the characteristic of your experiment and on your sensors.
So did you learn this in your class from
No.
aeronautics?
I learned it with Manny, studying and looking for applications of
Yes.
his sensor.
So I'm learning too. Piyush, were you familiar with this correction or? Okay, well, let's thank you again, Manny.